totally does, but it's not a big deal. I would have gotten 2e to the negative 3t plus 6e to the negative 3t is 8. I mean, it's still like terms before or after the inverse Laplace transform. It's still like terms, of course. Do you guys get that? So it wouldn't have been wrong if you didn't. If you did this part and then you did this part, you go, oh,
So
there you go.
Probably save that part like last. We're not doubling up.
Yeah, don't inverse Laplace because you might get some stuff to cancel, right? That'd be kicking ass. You don't have to worry about it. Now, how do you handle this?
Separate.
Yeah, because S stuff over this is the asshole cosine, and number over this is the all too nice sine, right? So you just have to be careful about, so this is not too bad. Negative 2 times S over S squared plus 4. Plus, now what do I want to have over my S squared plus 4 for sine to work correctly?
3 times.
What's supposed to be up here?
2.
2. So then out here is going to be 3. I'm like, yeah. See, I mean, that feels sort of like an interval kind of thing, or, I wonder why. So then this is going to be, and of course I got this here. So when I do my inverse Laplace, I get y of t equals negative 2 times cosine of 2t plus 3 sine 2t plus 8e to the negative 3t. And of course, you could solve this relatively quickly the other way, right? There's a few different ways you can solve that. I don't know if you guys realize you can do here's your e to the negative 3t. Now, I would have had to put a c in front of it and then figure it out later using this, but it's all part of the process here. See, that c becomes 8 to make this work. Do you guys see that? That there's the auxiliary equation, right? N plus 3 equals 0. That's the auxiliary. And then I can a sine 2t plus b cosine 2t and then do all that shit. Do you see how this is actually, well, I don't know if this is quicker, but you start to see how it could make some things quicker, for sure. Some things we've done already. And it makes other things we haven't done possible sometimes. Okay, so here's the new stuff for tonight. That was, believe it or not really old stuff, but we still hadn't done some concrete examples of it. Section 7.3 starts with this idea. I'm going to have you guys just work this. So start from fundamentals, start fundamentals, and figure out what this is. This is 7.3. And we actually end up only doing the first half of 7.3. There's a whole part of 7.3 that's really, really nifty that just isn't part of our curriculum, but it deals with translations on the other side. Translations in S. This deals with translations in T. Or the other way around. So officially, what would this be? Integral?
0 to infinity. To the negative.
Yeah, just throw this. Whatever's in here gets thrown in to that spot right there. Now, what's the very first thing you can do with this?
But the exponent.
Yeah, so this will be e to the
A minus S.
Yeah.
times t.
And let me keep it like this, just to show you. So whatever happens at S before, S minus A is fundamentally the same thing. It's linear in S where the slope is 1. So the same exact thing's going to happen, right? So this is going to be f of S minus A. Because what did I get before? What did I get just for this? I got big ass f of s. Because there's an s there. So what am I going to get now? Big ass f of s minus a. I've translated the function over. Now, what's the usefulness of this? Well, we saw a problem. I can't remember where it came up from. And I said there is a way to solve it. Let me see. But I think it was, I think it was this. Hold on. Crap. I need like a board-sized eraser sculpture. No. I think it was something like, shoot. What was it, Jeff? You could do it. Was it something like that? Shoot, I can't remember now. I could just steal one from out of here. All right, that's better. Well, that doesn't matter, Jeff, but it would be a little easier if this was just a 1. All right. Make that a 1 on top right now. So before, so we saw something like this before. And I said there was a way to do it. Pull this off to the side, complete the square, and do some stuff. So let's get some motivation as to why that would make sense. So let's do this. Here's some motivation. What would the Laplacian of e to the at t, e to the at, what would that be? Well, what's the Laplacian of t?
1 over s squared.
So what would the Laplacian of t e to the at be? All this does is, it's no longer s there, but now it's s minus a. So let me put a number here. Let's make it 4. So now it's going to be 1 over s minus 4 squared, right? All right, let's try another one. So whatever that would be, this translates it by that much. Actually, it translates by that much, because how much would this move over on the s-axis in which direction? 4 to the right. Of course, right? Because what does s have to do to overcome the minus 4? It's got to become 4 bigger. That's how I explain why it moves the other direction, right? Your inputs have to become 4 bigger to overcome me taking 4 away from them. That's why it goes the other way, So if there's a minus, who gives a shit, right? Yes, ma'am?
So it translates it because it's multiplying the t.
Yeah, anytime I have one of my regular functions multiplied by e to the constant t, this piece is the translator. Whatever that is, that moves over by 4 on the s-axis, period. So what would this be? What's the, somebody remind me, look it up, what's the Laplacian of cosine 3t? Or if you remember.
S over
Yeah.
s over s squared.
So what's the Laplacian of e to the negative 2t cosine 3t?
S over s.
No? S plus 2? Over? Yeah. So every s just gets translated over 2. Or, in this case. Now, of course, the more comfortable you get with Laplacian in the first place, and then inverse Laplacian, then you can try to tackle translations of those, right? Because now what's going to happen is I'm going to start here, I'm going to have to do an inverse Laplace. So that's like this guy. So what the shit do I do with this then? Well, exactly what I said earlier. What did I say earlier? Yeah. So this will be the inverse Laplace. So s squared plus 4s, what do I have to add to make that work? All right, let's try it. Let me help you out. 4s plus something plus 6 minus the same thing. All right, complete the square. Yeah, you have to add 4 to make this a perfect square, so you better subtract 4 at the same time, right? All right, now this is not going to come out pretty, but oh well, we should be used to non-pretty things. So what happens now, let's see, we get inverse Laplace, 1 over s plus 2 squared plus 2. Now, what I always used to do is this. This is going to be, what's this translation going to work back into? E to the negative 2t. And then I can focus on this. I've taken the translation out, and now I can focus on this. And I don't think the book shows this way to do it. There are some little, stupid little, oh, it's not exactly, who gives a shit? Get the translation taken care of. Now what's this going to be? It's not pretty, who cares? Sine. So you negative 2t sine square root of 2t. Right, because it's square root of this. This is k squared. You guys see the considerations you have to make to transform it into a form that works with translations. Now, translations opens the door for a lot more forms to work. It also opens the door to, well, how can I tell when it's a translation or something? That's just part of the process. Okay. Any questions about that example? Yes?
If you took the Laplace of sine root 2t, would it be root 2t over s squared plus 2? Since it's supposed to be, the k is supposed to be on top of the sine.
No, cosine is the one that gets the, k. Oh, yeah. Thank you. So what should be here? There's a little adjustment I have to make up here. This is supposed to be rad 2. So yeah, thank you for that, man. So then it should be that. So this little thing about, this is a lot like what we do with integrals, right? If we're missing something, we can put it in there if we balance it back out. So like you said, it should be k over s squared plus k squared. So this needs a rad 2, so I better divide by rad 2 out front. Like, very nice. It's a really good thing. I'm letting you use those tables. For me, it's kind of sucks a little bit because I remember it's been so long since I taught this course, and when I took it, I love Laplaces, and I just memorized the hell out of all of them. And now I was looking back, and I'm like, oh man, I kind of forgot all of them. So that's why I'm not going to make you memorize them, because I would still have to go back and memorize them myself, right? I never make you know things I don't know. Okay, I think, yeah, so there's a whole second half to 7.3 we don't do. It's translation on the t-axis. If you're curious, you can take a look at it. Their notation they use and the way they do this, I don't necessarily like it myself, but you can look at some of the examples and see if you like that notation better. They use this weird little s goes to s minus a. I'd much rather show myself what the hell's going on, pull the translation piece out, and then work with what's left. That just makes so much more sense to me. Okay. I think that might be enough for today. I wanted to head out a little early. I guess I am a little early.
What's that extra credit?
6.3. There were earlier ones, but I can't remember what they were. Everybody got a practice test, right? Okay.